So in our previous lesson, we saw how we can use arithmetic operators to perform mathematical calculations in our program. Albert, who is a student of my code school, is very delighted that now he can write programs to solve mathematical problems. He has written a simple program to find product of two numbers in which he is asking the user to input two numbers A and B, and then he is simply printing the product of these two numbers. Albert wants to run this program for A equal to 100,000 and B equal to 200,000. But when he's running the program, passing A as 100,000 and B as 200,000, he's getting this, a negative value for product of these two positive numbers. Albert is puzzled. How can the machine be wrong? Or is it his code that's gone wrong somewhere? There's not much in the code. Code looks alright. In fact, the code is working when Albert is passing smaller values for A and B. It's only when he's passing high values for A and B, he's getting incorrect output. As you can see, once again, for A equal to 300,000 and B equal to 200,000, we have got a negative value for product. Albert is unable to understand why this is happening. Can you make a guess to why this is happening? Well, to understand this, we need to go back to the basics of how data is stored in computer's memory. Let's say this figure that I've drawn in right here is computer's memory, and whenever I say memory in context of programming, I mean the main memory or random access memory or RAM. Now, as we had discussed earlier, at lowest level in its architecture, in its actual physical design, machine understands only binary. All the communication happens in binary and all the data is stored in binary. So whatever data has to go into the memory has to be encoded in binary. It's easy to think of numbers getting encoded in binary because binary itself is a number system. As we know, binary is a number system in which we can have only two digits, 0 and 1. But it's not so intuitive to think about other data types getting encoded in binary. Computers deal with all kinds of data. Text, images, audio, video, and everything is encoded in binary. We'll talk about how other data types get encoded in later lessons. In this lesson, we'll talk only about integers. A binary digit is called a bit, and a bit is the lowest or most basic unit of information in computing or digital communication. A bit can have only two values, 1 and 0, and these two values can be interpreted as true and false, or yes and no, or on and off, or anything else that can have only two values. A bit can physically be implemented with anything that can have two states. It can be flip-flop in a switch, or two distinct voltage or current levels in a circuit, or magnetic polarization. There are multiple ways of simulating a bit in physical design of things. Now, even though a bit is the lowest or the most basic unit of information, memory in a typical architecture is organized as a collection of bytes. 8 bits make a byte. In the logical representation of memory that I'm showing here, we have these segments or partitions, and let's say each segment here is 1 byte of memory. So we can store 8 bits in each segment. There would be many more bytes in the memory. That's why I'm showing it extending towards bottom and top. If my machine has 1 gigabyte memory, then 1 gigabyte is 2 to the power 10 megabytes, and 1 megabyte is 2 to the power 10 kilobytes. So 2 to the power 10 megabytes would be 2 to the power 20 kilobytes, and 1 kilobyte is 2 to the power 10 bytes. So 2 to the power 20 kilobytes would be 2 to the power 30 bytes. In this memory diagram, I'm showing less than 10 bytes. So you can say that I'm showing only a section of the memory, and that's why it's extending towards bottom and top. In a typical architecture, each byte in the memory would have an address. Let's assume that somewhere deep down here, we have a byte with address 1, and the address is increasing as we are going towards top. Let's assume that this particular byte has address 200. So the next byte would have address 201, and the next one would be 202, and the next one would be 203, and we will go on like this. Memory can logically be viewed as a linear collection of bytes where each byte would have an address. Machine keeps track of what part of the memory is free and what part of it is allocated, and if it's allocated, to which application it's allocated, because memory is a shared resource. It's shared by all the applications running on the machine. Please note that what I've drawn here is only a logical representation of memory. In this figure, address is increasing from bottom to top. We could also draw the memory something like this, where address is increasing from left to right. This left to right representation is often better to explain some of the concepts. Okay, now coming back towards our original question. When we declare a variable, we basically reserve some amount of memory to store some data. The amount of memory reserved will depend upon the data type, the compiler, and the machine architecture. For int in a typical architecture, we get 4 bytes. I have written a statement here to declare an integer named a. Let's say for this variable we have got a block of 4 bytes starting address 203 in this memory. We always get a contiguous block of memory for a variable. Having bytes scattered at various locations in memory does not make sense anyway. Now I'll write another statement here, and with this statement I'm filling in value 12 in this block of memory. So how will you write 12 in binary in 4 bytes or 32 bits? 12 in decimal or base 10 is 1100 in binary or base 2. I'm assuming that you know how to convert decimal to binary and vice versa. If you want to revise some of these concepts, you can check the description of this video for links to some lessons. Okay, so 12 in decimal is 1100 in binary, and this is how I'll write 12 in binary in 32 bits. 4 rightmost or 4 least significant bits will be 1100, and all leading bits will be zeros. Leading zeros do not matter. In binary representation, we call the rightmost bit the least significant bit, and we call the leftmost bit most significant bit. Let's say 8 rightmost bits is byte 1, and the next 8 bits or the next byte towards left is byte 2, and we are going further left as byte 3 and byte 4. Byte 1 is the least significant byte, and byte 4 is the most significant byte. Now what I want to do is I want to fill in these bytes in the memory block for A. Where do you think byte 1 should go? Well, we can have something like byte 1 can go to the smallest address, that is 203, and then byte 2 can go to 204, byte 3 can go to 205, and byte 4 can go to 206. Or it can be the other way. Byte 1 can go to 206, byte 2 can go to 205, byte 3 can go to 204, and byte 4 can go to 203. Both arrangements are possible. If least significant byte is given smallest address, such an architecture is called Little Indian architecture. And if least significant byte is given the highest address, then such an architecture is called Big Indian architecture. So which byte should go where will depend upon the memory architecture, whether it's Big Indian or Little Indian. Let's assume that our memory here has Little Indian architecture. So byte 1 will go at 203, byte 2 will go at 204, byte 3 will go at 205, and byte 4 will go at 206. So this is how data gets stored. As you can see, we get finite space in the memory for a variable. Depending upon the data type, we get a block of memory containing some bytes. Byte is the lowest unit in memory. Minimum memory that can be allocated is 1 byte. Now if we get finite space for a variable, then we cannot store infinite number of values in it. There would be a limit. So how much can we store in 4 bytes? Let's deduce this step by step. How much can we store in 1 bit? We can have only 2 possible values in 1 bit, 0 and 1. Now how much can we store in 2 bits? With 2 bits we can have 4 possible values, 0, 0, 0, 1, 1, 0 and 1, 1. Now with 3 bits we can have 8 possible values. we can have 8 possible permutations and combinations of 1 and 0. For each bit position we have two choices. We can either have a 0 or a 1, and corresponding to these two choices we have two choices for the next bit position, and corresponding to a combination of these two positions we'll have two choices for the next position. So with 3 bits we can have 8 possible values. With a given number of bits we'll get the minimum when all the bits will be set as 0, and we'll get the maximum when all the bits will be set as 1. And of course we can have all the values in between. In general, with n bits we can have 2 to the power n possible permutations and combinations of zeros and ones. We can have decimal values from 0 to 2 to the power n minus 1. As you can see, for n equal 3 we have values from 0 to 7. 2 to the power 3 is 8, and 8 minus 1 is 7. So with 4 bytes or 32 bits we can have decimal values from 0 to 2 to the power 32 minus 1. So if we have 4 bytes to store an integer, then the maximum value that we can store is 2 to the power 32 minus 1. But this is if we are storing only positive values. Int data type can store negative values also. If we are storing negative values also, then the maximum cannot be 2 to the power 32 minus 1. First of all, how do you think we can store negative values in binary? One of the things that we can do is we can use one of the bits to store the information that whether it's a positive number or a negative number, and we can use rest of the bits to store the magnitude or absolute value. So if we have 32 bits we can do something like this. We can use the leftmost bit or the most significant bit as sign bit to store the information that whether it's a positive number or a negative number. It can be something like if the most significant bit is 0, it's a positive number, else if it's 1, it's a negative number. And we can use rest of the 31 bits to store magnitude or absolute value. If we will do something like this, if we will use the most significant bit as sign bit, then half of the notations in a given number of bits would be positive values and half would be negative values. If we have 3 bits and if we are using the leftmost bit as sign bit, this is how things will look like. With this encoding mechanism, with n bits, we can store values from minus 2 to the power n minus 1 minus 1 to 2 to the power n minus 1 minus 1. Because we are using n minus 1 bits for magnitude, so the maximum magnitude that we can have is 2 to the power n minus 1 minus 1. And because now we also have a sign bit to say whether it's a positive number or a negative number, so the maximum negative value that we can store would be minus 2 to the power n minus 1 minus 1, negative of the maximum possible value. This encoding mechanism looks good, but it's not used because there are some issues. First of all, there are two notations for 0, 0, 0, 0 and 1, 0, 0. Both are 0. And another problem is that we cannot apply simple rules for binary arithmetic. For example, we add two numbers in binary just the way we add two numbers in decimal. Let's say we want to add these two numbers 001 and 101. We need to start at the rightmost position. We need to find the sum of the digits, and if the sum is greater than 1, we need to take a carry. Here sum of these two digits would be 10, that is 2. So we'll keep a 0 here and take 1 as carry to the next position. And now we'll go to the next position. Here the sum of digits and the carry is 1, so there is no carry for the next position. And for the leftmost position also, the sum of the digits, the bits and the carry is 1. So if we are performing normal binary addition, this is what we have got. But see that 001 in this encoding system is plus 1 and 101 is minus 1, but the sum here is not 0, it's minus 2. So clearly normal binary arithmetic is not working. It was difficult to design circuits for arithmetic operations with this encoding mechanism. So machines use another encoding mechanism, and it's called 2's complement system. When we simply invert all the bits in a binary number, then it's called 1's complement of that number. And adding 1 to the 1's complement gives us 2's complement. In 2's complement system, negative of a binary number is stored as its 2's complement. This is how things will look like in 3 bits if we are using 2's complement system. Now, once again, with this system, most significant bit of all the negative numbers would be 1, and most significant bit of all the positive numbers would be 0. So here also we can call the most significant bit sign bit, because by looking at this bit we can decide whether it's a positive number or a negative number. And in this encoding mechanism we have only one notation for 0, and what's more interesting is that we can apply rules for normal binary arithmetic. So now if I'm adding 0, 0, 1, which is plus 1, and 1, 1, 1, which is minus 1, and then let's see what's happening. We'll start at leftmost position. 1 plus 1 would be 1, 0. 1 will go as carry. Now at the next bit position we once again have two 1s, so 1 will go as carry, and once again for the leftmost position also we'll have a 0 and 1 will go as carry. So actual result would actually be 1, 0, 0, 0, but because we are storing the numbers in 3 bits only, we do not have space for 4th bit, so this leftmost 1 should actually go in an overflow. And if we are keeping only the 3 zeros, then our result is 0 as expected. In this system, if you want to revert the sign of a binary number, you need to find its 2's complement. So 101 is 2's complement of 011, and 011 is 2's complement of 101. You can quickly do the maths and check this. In 2's complement system with n bits, we can store values from minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. If we'll compare this to the previous encoding mechanism that we were trying, we are able to store one more value here because we do not have two notations for 0. If you want to know more about 2's complement notation, you can check the description of this video for a link to some resources. Now, because with a given number of bits, we can only have values in a certain range. For example, if n is 3, then with this encoding mechanism we can have values from minus 4 to 3. So if result of an arithmetic operation is not lying within this range, we'll get an incorrect output because of an overflow or something else. Now with 32 bits we can have values from minus 2 to the power 31 to 2 to the power 31 minus 1. Albert was trying to multiply 100,000 and 200,000, and the product of these two numbers, which would be 2 into 10 to the power 10, is greater than the maximum value that we can store in 32 bits. If you remember, upon running the program we were getting this value minus 1474836,480. Now I'll show you something interesting. I have opened calculator on my Windows machine, and from the view menu I have selected programmer mode. Now I have entered 2 into 10 to the power 10 here, and I'll convert this to binary. I need to click on this binary bin radio button here. So this is 2 into 10 to the power 10 in binary. Now I have written 2 into 10 to the power 10 in binary here. We have 35 bits here. What I'll do is I'll ignore the 3 most significant bits and I'll calculate the value of these 32 bits. Now if I'm looking at these 32 bits in 2's complement system, then this is a negative value because the most significant bit or the sign bit is 1. If we will calculate the 2's complement of this number, we will get the magnitude. First I have calculated 1's complement here, and now I'm adding 1 more to calculate 2's complement. This is what I've got. Now I have opened my calculator and I've selected binary here so I can enter a binary value, and I've entered this value, and now I'll convert this to decimal, and I'm getting 1474836,480. This is the magnitude of our negative value. So if you can see, because of the overflow, the result that got printed was the value of rightmost 32 bits. I hope this is making some sense. So in programming, when we use a data type, we need to know our limitations with it. So as we discussed, int in a typical architecture would be 4 bytes, and we can store both positive and negative values in int. Values are stored in 2's complement notation, and we can store values from -2 to the power 31 to 2 to the power 31 minus 1. We can choose to store only non-negative values in our integer variable. We need to use this keyword unsigned before int in our declaration, and now my variable will store only non-negative values. The range of unsigned int would be 0 to 2 to the power 32 minus 1. Size, once again, in a typical architecture would be 4 bytes. In case of unsigned int, binary value will be interpreted as it is and not through some other encoding mechanism like 2's complement notation. So we can have signed and unsigned integers, and of course the range is different for these two. Now, as we saw earlier, 4 bytes or 32 bits was not good enough for us when we were multiplying 100,000 and 200,000. If 4 bytes is not enough, we can use another type called long int or just long. And with long you'll get 8 bytes. There is no difference from int except that you're getting twice the memory. Long can also be signed or unsigned. With signed long, our range would be -2 to the power 63 to 2 to the power 63 minus 1. Negative values will once again be stored in 2's complement, and the range of unsigned long would be 0 to 2 to the power 64 minus 1. 2 into 10 to the power 10, which was result of our previous multiplication, would easily fit in a signed long. Now in this program that we had written earlier, I'm declaring a, b and c as variables of type long, or I can also say long int. Placeholder for long or long int is %lld. So as you can see in scanf and printf statements, I'm using %lld as placeholder. When I'm running this program, passing a as 100,000 and b as 200,000, I'm getting 2 into 10 to the power 10 as output now. There's one last thing that I would like to mention. Size of a data type can vary with compiler and machine. In C, there is a function to find size of a data type. This function sizeOf returns size of a data type in bytes, and you can pass the keyword for the data type to this function. So as you can see, I've called sizeOf function, passing it this keyword int. Upon running the program, this is what I'm getting. Let's change this int to long. For int I was getting 4 as output, and now for long I'm getting 8. You can use this function to know the size of any data type. I'll stop here now. In next few lessons we'll get to know other data types. This is it for this lesson. Thanks for watching.